Hello guys, how are you today? So today I'll be explaining the past papers for physics. We have 8 past papers, but not all of the questions. So we're gonna start with question number 2 from paper 4, October-November 2023. Figure 2.1 shows an electric tumble dryer used to dry wet clothes. We have the drum inside, we have the clothes, we have the condenser, hot air flows into drum, heating element, and cool air leaves the condenser. So basically what's happening is that you have water in here. What's happening is that the water is gonna cool the hot air because we're having air flowing inside of the dryer. The air, because it is cooled by the water, it will come from here, okay? It will enter through the heating element, it will get heated, and then it will go as hot air into the dryer. And then it will return here, and it will be cool again by the water, so it will cool down. So now, if we go down to answer the first question, hot air blows into the drum. The air gains water vapor from the clothes and then leaves the drum. The moist air enters the condenser. Cool air leaves the condenser, passes through the heating element, and enters the drum again. State the process by which hot air removes water from the wet clothes. What's happening is that the water is entering from here, and it is really hot. So they're telling us, what's the process that the hot air is removing the water? The water is usually cooled from the clothes, but because we have hot air, what's gonna happen is that it is gonna evaporate the air. Not the air, sorry, it will cause the water to evaporate. So the process used over here is evaporation. So evaporation. Okay, we move on to part 2. The air is cooled as it passes through the condenser. Describe and explain one other way in which the air leaving the condenser is different from the air entering the condenser. So the air from over here takes the water. So that means the air is what? Is wet. We have wet air. Now when it passes through the condenser, all the liquid will, from evaporation, it will cool down and become water again. And then it will come here again, but it is dry. It does not have water with it. So the first thing is that it is drier. So we say that the air is drier. Now, how exactly did the air become drier? So if we go up again, as we said, the hot air will take the water with it. It will come here, and here, when the water when the hot air, which has the evaporated water in it, cools down, it will turn into water. It cools down by condensation. So very simply, we can say that the water, okay, water vapor becomes condensed. All right, we move on to part B. The drum of the tumble dryer rotates, lifting up the wet clothes, which then fall down through the hot air. So if the clothes become here, okay, it will fall down. Why? Because it has a weight and the gravity is pulling on it. So what is the force that causes the clothes to fall down? You can either write the gravitational force or the weight. Okay? Now, when the drum rotates too fast, the clothes remain in contact with the wall of the drum. State the direction of the resultant force on the clothes during the circular motion. So what happens is we're going to use something we learned last year. You remember Newton's explanation on how a satellite stays in orbit around the Earth? He said this is the Earth, this is the atmospheric layer, okay? And this is the satellite. The direction that the satellite moving in is like this. But there is another force, which is usually the force of weight, that is perpendicular to the direction of the motion of the satellite. It has to be exactly perpendicular, and when it is perpendicular, this force over here will not work, and this force over here will not work, so instead it's just gonna go in a circle. So what's happening is that if you have clothes over here, the direction of motion of the clothes is, let's say, like this. Okay, it's gonna go and then turn and whatever. But then, what is a perpendicular force to it? It is the weight. So because it is perpendicular, this force is not gonna work and this force is not gonna work, so it's not gonna fall down, it's gonna stay up and it will continue moving around a circle. So the direction of the force always has to be perpendicular to the direction of motion, or to the motion, however you want to write it. Now we move on to part C. Suggest why using a clothesline to dry clothes in the open air is better for the environment than an electric tumble dryer. Anything better for the environment, okay, is anything that does not use electricity, because the electricity might contain fossil fuel. So your answer has to be a complete answer, okay? You could write it like this. You can either say that the solar energy that's using to dry the clothes is renewable, or you can say electricity, or the electric dryer uses fossil fuels, okay? Whereas the sunlight or the wind are renewable resources. So if you write it like this, you are gonna get the full mark. So this is the first past paper done. Now I'll move on to the second one. So now the second past paper, which is paper 4, May, June 2023, we have questions 4 and 5. Now, temperature of a fixed mass of gas at constant volume is decreased. State and explain in terms of particles how the pressure of a gas changes. In terms of particles, this over word. Whenever we're describing the how the pressure of a gas changes in terms of particles, and look what they told us. They told us the volume is constant, but the temperature decreases. So we are applying who? We are applying, not Charles' law, we're applying the pressure law, okay? So the pressure law states that the temperature is directly proportional to the pressure. So if we are gonna write an answer to get the full 3 marks, okay, it is gonna be that as the temperature decreases, of course you have to write fully decreases, I'm just shortening it, the kinetic energy of particles, you have to write particles, this is very important, decreases, okay? So their collisions decrease, and since the collisions decreased, we say that the pressure decreases. So like that you get the full 3 marks. Now they're telling us state the value of absolute 0 in degrees Celsius. You should know absolute 0 Kelvin is equal to negative 273 degrees Celsius. So the answer over here is negative 273 degrees Celsius. If you can't memorize it, I saw a joke on the internet. It's like a really bad joke, but it will help you memorize. It was like a chemist froze himself at negative 273 degrees Celsius. And then someone was like, oh, is he alright? And then the other person was like, yes, he's okay. So okay, 0 Kelvin is negative 273 degrees Celsius. Now, we need to explain what is meant by the term absolute 0. Absolute 0. Okay, please remember that. Absolute 0. To get the full 2 marks, okay, you have to write that it is the particles. It is where the particles of an ideal gas have little to no kinetic energy, okay? And it is the lowest temperature possible that can be reached, okay? Of course, write it in full words. I'm just writing it like this so it can be quicker. Now, for part C, we have cylinder 1 contains 350 centimeter cubed of gas at a pressure 9.0 times 10 to the power of 4 Pascal. The gas is transferred to cylinder 2 and the pressure increases. So let's see what we have. The temperature, first of all, remains constant. So we are using Boyle's law, okay? We have our volume initial, or volume 1. Then we have our pressure 1. We have our pressure 2. Now we need to find our volume 2. Boyle's law states that PV equals constant. So then P1 V1 equals P2 V2. Okay? So we have pressure 1, which is 9 times 10 to the 4, multiplied by volume 1, which is 350. It is then equal to pressure 2, which is 1.6 times 10 to the 5, multiplied by volume 2. To find volume 2, it is going to become 9 times 10 to the 4 times 350 divided by 1.6 times 10 to the power of 5. So doing it, you are gonna get approximately 196.8, which is almost 197. Now in the answers, they wrote it as 200, so I believe that they rounded it to 200. So you're right, 197. Of course, you have to solve, but 197 rounded, it is 200. Okay, also, I just saw there is another way where they did 1.97 times 10 to the power of 2. So then if you write either this or this, you will get it correct. Now we move on to question number 5. Figure 5.1 shows an electric heater used to heat a room. The dimensions of the room are 4.5 times 6.1 times 2.4 meters. The density of the air is 1.2 kg per meter cube. They need us to show that the mass of air in the room is 79 kg. Very simply, we know that mass over volume is equal to density. We can find the volume. We have the density, so then we will be able to find the mass. Very simply, what you have to write in the exam is that mass over volume is equal to density. Okay? You have density, which is 1.2 kg per meter cubed, is equal to the mass that we need to find over the volume, which is 4.5 times 6.1 times 2.4, which is, all in all, 65.88. Now, to get the mass, you just need to multiply this by this. You are going to get then that mass is equal to 65.88 times 1.2. You're going to get 79.056. Rounded, it's approximately 79. Now, we move on to part II. The power of the heater is 1100 watts. Specific heat capacity of air is 1000 joules per kg times degree Celsius. We need to calculate the time taken to increase the temperature of air from 16 degrees Celsius to 20 degrees Celsius. Okay, so let us write our given. We have our power, which is P. We have specific heat capacity, which is C. We have delta T, which is 20 minus 16, which is 4. And if you go up, you can use the mass from here, 79 kg. And we have that mass is 79 kg. So now very simply put it into an equation. Power times time is equal to Q. Q is equal to MC delta T. So that means power times time is equal to MC delta T. Substitute 1100 times the time is equal to 79 times 1000 times 4. Okay, solving for the time, you're going to get that time is equal to 1000 times 79 times 4 divided by 1100. Do it on your calculator. You are going to get 287 seconds. Now again, you can either write it like this or you can round it, and it's going to be approximately 290 seconds. So that's part II done. Also write the answer here, 290 or 287 seconds. Now we go down. They're telling us, suggest one reason why the time calculated in AII is the minimum time needed to increase the temperature of the air in the room from 16 degrees Celsius to 20 degrees Celsius. Very simply, remember that all of this heat, this energy, does not only go to the air of the room, it's also lost to the surroundings. So heat may be lost to surroundings, such as, for example, if you are in a room that has a couch, it might lose heat to the couch, or furniture, it might lose heat to the furniture, or if you are in a room with people, it might lose heat to the people. So heat may be lost to surroundings. Now part B. Figure 5.2 shows a cross-section of a double glazed window in a room. State the main methods of thermal energy transfer from the room to outside which are reduced by this type of window. what happens is that you have here some air particles. Let's say here in the UAE we have hot air outside, and we like to keep it cold on the inside. So inside here it's cold air. Notice how I made the cold air particles bigger? It's because cold air is denser, so it has a bigger volume. Now what we have inside of here is air. So over here we have air. So this is air. Air is the worst conductor, first of all. So definitely the heat from outside is not going to enter inside because air will stop the conduction. Second of all, because it is a solid, it's not gonna have, because it's passing through glass, it's not gonna have convection. So pay attention to this, okay? The methods, they said the main methods, so you have more than one method. First of all, what are your three methods of thermal transfer? You have convection, conduction, and radiation. Radiation passes through all matter, so directly we cross radiation out because it is not reduced at all, whereas conduction and convection can be reduced. So our answer are conduction and convection. So this is the last part, I believe. Yeah, so now I'll move on to the third past paper. Now here we have only question number 3. They told us tidal power derives most of its energy from the moon and part of its energy from the sun. State one source of energy or one source of power which derives its energy from the sun. So I'm gonna write fossil fuel. Why fossil fuel? Because fossil fuel from before they were plants and animals. Plants and animals got their main energy from the sun. Mainly plants get their energy from the sun. And then when it will transform it to chemical energy. So this is kind of derived from the sun. Alright? Now state one source of power which does not derive its energy from the sun. One very easy one is nuclear. You can also say geothermal. So nuclear or geothermal. Nuclear because it does not depend on the sun. Actually, nuclear reactions happen on the sun, okay? And geothermal energy is the heat of the earth. So it's not the heat from the sun, it's the heat of the earth. So we're gonna go down. Figure 3.1 shows a small water turbine driven by a tidal flow of water to generate electrical power. Explain whether this method of generation of electrical power is renewable. Yes, it is renewable because water is a renewable material. Okay, writing yes on its own will give you half of the mark, but you have to explain. So yes, because water is not consumed. You can say this, or it's always renewable, or it's not used up. Now part 2. The mass of water passing through the turbine each second is 6 times 10 to the 3 kg. The speed of water is 2 meters per second. 40% of the kinetic energy of the water is converted to electrical energy. We need to calculate the electrical power generated. First of all, power is equal to Q over T. Q means work. So you can substitute Q by W. So then power is equal to work over time. Another thing we know is that the work is equal to the change in kinetic energy. So here they didn't give us initial velocity, so we are going to state that it's 0. So if initial velocity is 0, we're going to have that work is equal to kinetic energy final minus kinetic energy initial. But then kinetic energy initial is going to be 0. Why? Because the velocity is 0. Because kinetic energy is equal to 1 over 2 mv squared. If the velocity is 0, then it is all 0. So that means the work is equal to the kinetic energy final. Okay? So then the work is equal to 1 over 2 times the mass, which is 6 times 10 to the power of 3, okay? Times the velocity, so times 2 squared. Doing it on our calculator, we are gonna get 1,200, or sorry, no, 12,000. My bad, it's 12,000, So we didn't really need to find the work because I just read and they said that 40% of the kinetic energy is converted to electrical energy. We found now the final kinetic energy, which was 1 over 2 times 6 times 10 to the 3 times 2 squared, and we got 12,000. Okay, now we do what? We multiply the kinetic energy we got, which is 12,000. We multiply it by the percentage, which is 40 over 100. Doing it, you are gonna get 4,800 watts. Don't forget your unit. So your answer here is 4,800 watts. Now we move on. We finished, I think. So yes, we finished the third past paper. We'll move on to the fourth one. Okay, in the fourth one, we have questions 4 and 5. Now, a power station uses wind energy to generate electricity. State and explain whether this method of generating electricity is renewable. Definitely it is renewable, so just write renewable or yes. Now the explanation, very simply, just write wind is not consumed, and like this you get both marks. Now we go down to part B. State two energy resources that do not have the sun as their source. We answered a question like this. So it was geothermal and nuclear. Now 4C. For each energy resource, state the form of energy stored. In fossil fuels, it is chemical energy, but if you go back all the way to the origin, it is what? It is sunlight energy. Now, the water behind hydroelectric dams, it is the gravitational potential energy. Don't write potential, okay? Potential energy. Don't write potential on its own because it could be elastic potential, vibrational potential. No, we need what? We need the gravitational potential energy. So you have to write gravitational potential energy. Now we move to number 5. A thermocouple thermometer is used to determine the temperature difference between a mixture of ice and water and liquid mercury at approximately 600 degrees Celsius. Complete figure 5.1 with a label diagram to show how the thermocouple thermometer can be used in this way. Okay, so you can draw it like this. You will have a junction here and here. So this is one wire, so don't forget to label your wires. Then you have something like this, like this. These are another wire. And then most importantly, don't forget to draw the galvanometer. You can draw it with an arrow like this. So label your wires, so you can say wire A, wire B, wire C. Then you can write on the side note over here, wire A and B are of the same material. Okay? So if you draw it like this, it is considered correct. You get 3 points. Why? The 1 point is for drawing 2 different wires. Second is that you put each junction in a different liquid. And then the third one is the galvanometer. Okay? Now, state 2 other physical properties that can be used to measure temperature. Just think of any thermometric property. You can say electric current or electric resistance, anything to do with electricity, or the expansion of liquids. Part C, state 2 benefits of using a thermocouple instead of a liquid and glass thermometer. First of all, a thermocouple has a high heat range because a liquid and gas thermometer might break at extremely high temperatures, whereas a thermocouple thermometer can measure high heat range. It also has a low heat capacity, means it will react quickly. Okay? Alright, so I think we finished the fourth past paper. Now we will move on to the fifth one. So here we have only one question, which is question number 4. Figure 4.1 shows a metal pan on an electric hot plate. The pan contains 200 centimeter cubed of water. The pan is heated. The temperature of the water in the pan increases. Thermal energy is transferred through the metal pan by conduction. Now state and explain the 2 ways that thermal energy is conducted in a metal. You can say that the particles collide with nearby particles, causing an exchange in thermal energy. Okay, this way, I remember it came in the AMS, it is the slower way of heat conduction, or by free electrons moving through the metal. Okay, so if you write these two, you are gonna get the 3 marks. You're gonna get 1 mark for this, 1 mark for this, and 1 mark for this. So the particles collide with the nearby particles, causing an exchange in thermal energy. Free electrons is a point by itself, and that they move through the metal is also another point. Part B, the water boils and leaves the liquid as a gas. Explain in terms of forces and distances between particles why the gas occupies a much greater volume than it does a liquid. If you remember, we also took this last year. The more farther apart two objects are, the less their attractive forces are. So you can write the more farther away forces are, the less attractive forces between them. Okay, so you say this is for the gas, and in addition to that, you need to say that this is in the case of liquid. So if you write this, you will get the full 2 marks. The more farther away forces are, the less attractive forces between them. My bad, not forces. The more farther away particles. So the farther away particles are, the less attractive forces between them. So you have a particle here and a particle here. Definitely the attractive forces are stronger than if you have a particle here and a particle here, you know? Now, we need to state 2 ways in which boiling differs from evaporation. Evaporation happens at any temperature. Okay? And it happens, okay, this you can write evaporation. You have to state which one you are talking about. And then evaporation, of course, write the full thing, happens only at the surface. Whereas boiling happens throughout all of the liquid. So you have, for example, here, you have the liquids on the top. During evaporation, these particles only become gas, whereas during boiling, all of the particles, so all of it will become a gas. Now we move on to 4C. The water is replaced with 200 centimeter cubed of milk. This is our volume. The initial temperature of the milk is 20 degrees Celsius. The boiling point of milk is 95 degrees Celsius. Milk starts to boil when 60,700 joules of thermal energy has been transferred to it. Okay, so this is Q. The density of milk is this, so we can find the mass. We need to find the specific heat capacity of C. What do we have? We have delta T, which is 95 minus 20, which is 75 degrees Celsius. We have the volume, which is 200 centimeter cubed. We can find the mass by doing volume times density. So do 200 times the density. You are then going to get 206 grams. Pay attention because here it is grams. So of course, you have to change it to kilograms, so it becomes 0.206 kilogram. Now they need us to find C, and we have Q. Very simply, Q equals MC delta T. Q is 60,700. It's equal to the mass, which is 0.206 kilograms, multiplied by the C, which we need to find, multiplied by delta T, which is 75. Then, solving for C, you're going to get C is 60,700 divided by 0.206 times 75. And so then you are going to get 3928, rounded, almost 3930. So it's almost 3,930 joules per kg times degrees Celsius. Joules is our Q, kg is our mass, and degrees Celsius is the delta T. So now let's see, I think we finished this paper, so let's move on to the next one. Now for this past paper, which is paper 4, May-June 2021, we have only question number 2. Okay, we need to define the moment of a force. Very simply, what is moment? Moment is force times perpendicular distance. Okay, so if you're gonna write it, it is force times perpendicular distance from axis. Now we are gonna move on to part B. I remember part B, my teacher explained it to us. She was like, it has something we didn't take yet, so let us see. Figure 2.1 shows an object of negligible weight. The object is in equilibrium. The object is free to rotate about its pivot P. We need to find the value of force F. If it is in equilibrium, that means moment clockwise equal to moment counterclockwise. So we have this force F over here that we need to find. We have from the pivot a perpendicular distance of what? Of 12 centimeters. Now here we have a force what? We have a force of 500 newtons. How did I get 500 newtons? I did mass times G, so 50 times 10, 500 newtons. Now you may be wondering, oh, but it's not here, and how do we find the distance from the pivot? Very simply, the force that is here, because it is not moving, because it is in equilibrium, the force down, the weight, is equal to the force up, which is the tension. So the tension is then 500 newtons. And then the tension is the same all throughout the rope. So it's the same here, and here, and here. So now we have what? We have a tension over here, which is 500 newtons. Okay? So now we have a force, and we can find its perpendicular distance, which is 20 centimeters. So very simply, force times 12 centimeters is equal to 500 times 20. So force is equal to 500 times 20 divided by 12. It is gonna be 833.3. Dot dot dot, repeating, so they rounded it to 830. So the value of the force F is 830 newtons. Don't forget the N. Now we're going to move on to C. Describe an experiment involving vertical forces to show that there is no net moment on an object in equilibrium. You may draw a diagram in the space provided. Okay, to draw a diagram, first of all, one of the most basic ones is the seesaw. So if you can draw a seesaw like this, okay? And then you say the mass from over here, let's say it is 10 kg, so it's 100 newton from here. And let's say from here you have it 20 kg, so 200 newton. So now to get the distances, all right, you're gonna say the distance from, not from there, the distance from the weight to the middle or to the axis. Let us say it is then 2 meters. So then the distance from here to here is gonna be 1 meter. Now to solve it, you just have to write. Of course, don't do it like me because mine is not that good. You have to do it like this. So 2 meter, 1 meter. Now very simply calculated, do moment clockwise is equal to moment counterclockwise. So solving it, you are gonna get 100 times 2 is equal to 200 times 1. Then you will get 200 is equal to 200, and that's it. There is no net moment. So now just write in excess that object is balanced or is in equilibrium, okay, since net moment is equal to 0. Also, if you want, just for the an extra idea, draw a force going upwards. It should be equal to all the forces downwards. So 100 Newton plus 200 Newton, so that is 300 Newton. Okay? If you wanted to solve it, for example, from over here, let's say this point over here was our axis. How would you solve it that moment clockwise is equal to moment counterclockwise? Since you have the up force, it is gonna be all moment clockwise is equal to all moment counterclockwise. The moment clockwise is the 200 newtons, so it's gonna be 200 newtons times the distance from here to here, which is 3 meters, is equal to the moment counterclockwise, which is 300 newtons multiplied the distance from here to here, which is 2. And solving it, you're gonna get 600 equals 600. So either way, it is the same thing. And we finished this one. We finished May, June 2021. Question number 2, but I believe we have also question number 11. So let's go down and check it. 9, 10, 11. Here we have that a student investigates a radioactive substance in a laboratory. Figure 11.1 is a graph showing the count rate detected as the substance decays for 7.5 minutes. In part A, they're asking us determine the half-life of the substance. They told us what? That the background radiation is 20 counts per minute. So let's look at the graph and see what is the total counted radiation. It is 220. So the original radiation is equal to the total radiation, 220, minus the background radiation, which is 20. So you are gonna get 200. Okay, this is the initial, like the original radiation. Now, okay, so now they need the half-life of the substance. We have now the original radiation of the substance, which is 200, divided by 2, you are gonna get 100. Now at 100 radiation, let us find the time. Actually, this one is not too accurate. Okay, so we have that the original radiation is 100, and we know that the background radiation is what? 20. So this is what? This is the time with the background radiation. So what we're gonna do is we're gonna add the background radiation again. So now we have 120 radiation as total. So on the graph, we're gonna look for 120, which is over here, and it's approximately 2.4 minutes. So it took, the half-life of this substance is 2.4 minutes. Now we need to calculate the count rate detected at 9.6 minutes. So you go here, you are gonna look for 9.6 minutes, but we do not have 9.6 minutes. So what we're gonna do is we're gonna go down. Now this one is a little bit tricky, okay? But how we're supposed to do it is that you're gonna come over here, you're gonna take the last point. The last point that you see, for example, I see this over here. So 6.2. At the time 6.2, there was 50, a rate of, okay? Now what we are gonna do is we're gonna find the counts, because what they need in the question is the counts per minute. So we're gonna do, to find the counts, we're gonna divide the counts rate, which is 50, the counts rate over counts per minute. We're gonna divide it by the time per minute, 6.2. So 50 divided by 6.2 is 8.064, okay? Now what we're gonna do is that if 6.2 minutes gives us a rate of 8.064, how much will 9.6 minutes give us? So then we do cross multiplication. So 8.064 times 9.6 divided by 6.2, and you are gonna get approximately you are gonna get 12.5. So you choose either 12 or 13. I'm gonna put it as 13 counts per minute. Now, part B, the substance emits alpha particles and gamma rays. The student suggests that it's safe to store the particle in a plastic container of thickness 2 millimeters. State and explain whether the student's suggestion is correct. No, it's not. No, it is incorrect. Why is it incorrect? It is because the gamma rays, so gamma rays, are not stopped by a plastic container. They need to be put in a lead container, so gamma rays are not stopped by a plastic container. Okay, so this is this past paper. Now we move on to the next one. Now this is the next one over here. It's a very easy one. Define the moment of force about a point. Moment we know is force times perpendicular distance about the axis, so about axis or from the axis. Now we move on to part B. Figure 2.1 shows a uniform rod of wood suspended from a pivot. The rod is held stationary. Stationary means it is stable. That means moment clockwise is equal to moment counterclockwise by a horizontal force F acting as shown below. They gave us the mass of the rod is 0.08 kg. To find the weight, you are gonna do M times G, take G as 10, okay? So the mass, which is 0.08 times 10, gives us 0.8 newtons. Now, they need us to find the moment of W about the pivot. Very simply, the moment is the force times the perpendicular distance. The force W is 0.8 newtons. And the perpendicular distance, they helped us out. They told us it is 0.25 meters. So very simply, we're going to go down again. And the moment of W about the pivot is 0.8 times 0.25. The force times the distance. If you do it on your calculator, of course the force is always in newtons and the distance is always in meters. So 0.8 times 0.25, we are gonna get 0.2 Newton per meter. Okay, now we need the moment of F about the pivot. If we go up, so we know it is stationary. Since it is stationary, then the moment clockwise is equal to the moment counterclockwise. So look, this over here is our pivot. Let's find which one is the clockwise moment. The clockwise moment is the weight, and the counterclockwise moment is the force. So if weight is the clockwise moment and the force is the counterclockwise moment, that means the moment, and it is stationary, so moment clockwise equals moment counterclockwise. So the moment of the weight is equal to the moment of the, here it was 0.2 Newton per meter. So the moment of the weight is equal to the moment of the pivot. So it is also 0.2 Newton per meter. To find the force F, you're just going to apply force times distance equals force times distance. So we have, first of all, the force times distance 1, which is the moment 1, which is 0.2 Newton per meter, is equal to the force F that we need to find times the distance. What is the perpendicular distance from the pivot? It is 0.75 meter. So times 0.75 meter. Then applying the rule, we are gonna get that the force F is approximately 0.27 Newton. So here it is 0.27 Newton. Now part C, state whether the force F needed to hold the rod stationary must be increased, decreased, or stay the same if the angle between the rod and the vertical is increased. Okay, so I cleared it out to re-explain what's gonna happen. We increase the angle between the pivot and the weight. What's gonna happen is then the stick's gonna become like this, or no. To draw it better one time, good. Okay, this is now how the stick is. I know it's not the best drawing, but this is how the stick is right now. Now, because the weight does not change, the center of gravity is just gonna shift, okay? If they ask you how the weight is controlled, it's because the center of gravity is shifting. But what's gonna happen is that the distance between F, okay, and the pivot decreases. So we know that the moment of F stays constant, and it's equal to force times distance. If the distance decreases, that means the force is gonna increase. So to go down and answer it, we are gonna say, because the distance between F and pivot decreases, so F has to increase. The force F has to increase. If you write it like this, you are gonna get a full mark. But of course, write it full words. And this is all for this past paper. I believe we have, no, we also have question 5, never mind. So question number 5. Define specific latent heat. Specific latent heat is what? It is the energy, which is Q, needed to change the state of a substance, to change state. Specific latent heat, Q equals M, for example, LF, or Q equals MLE. Whichever of the two, they are needed to change a state. From LF, it is from solid to liquid. For LE, it is from liquid to gas. Explain the melting of a solid in terms of molecules and energy. When a solid melts, the bonds are broken. So we say the bonds are broken. Okay? So since the bonds are broken, for the bonds to break, they need energy. So energy is required. You can write it like this, or you can say melting is when the bonds of a solid break. To break the bonds, you need energy. Same thing. B. An electric heater is used to heat a liquid to its boiling point. Figure 5.1 shows the apparatus. Okay, when the liquid is boiling, the heater supplies 1.26 megajoules of thermal energy. The mass reading shown on the balance decreases from 3,800 grams to 2,300 grams. Calculate the specific latent heat of vaporization in the liquid. Okay, very simply, the specific latent heat of vaporization of a liquid is M equals M. Q equals M times LE. My bad, my apology. We have a heat which is 1.26 megajoules, which is in joules 1.26 times 10 to the power of 6 joules. This is Q, is equal to the mass. To find the mass, you do 3,800 minus 2,300. You're gonna get 1,500. Change it into kilograms. You are gonna divide by 1,000. You're gonna get 1.5 kilograms. It's equal to 1.5 times LE. Very simply, to find LE, do 1.26 times 10 to the 6 divided by 1.5. 1.26 times 10 to the power of 6 divided by 1.5. You are gonna get 840,000. Okay, to change it into scientific notation, it is then, I don't know what happened, it glitched. It is then 8.4 times 10 to the power of 5. Now we move on to part C. Also, don't forget the unit, it is joules per kg. Now part C, state and explain a precaution to improve the accuracy of the value of specific latent heat calculated in B. Here you get 2 marks, so you have 2 answers. The first answer is to prevent heat loss by insulation. Why should we prevent the heat loss? So that our answer is more accurate. Our answer is more accurate. So if you write it like this, you will get it correct. State and explain a precaution to improve the accuracy. You prevent heat loss by insulation, so that our answer is more accurate. Now we can move to the final sheet. This is the final sheet. A student investigates the cooling of water under different conditions. Figure 3.1 shows the setup. Thermometer in figure 3.2 shows the room temperature at the beginning of the experiment. Record 0R. Okay, they told us, let us find the room temperature. Very simply, by looking at the thermometer, you will get it is approximately 22 degrees Celsius. The student pours 200 centimeter cubed of hot water into a beaker. He places the thermometer in the water. He records the temperature initial of hot water at time t0. He immediately starts a stopwatch. He records the temperature at 30 seconds interval. The temperature readings are shown in table 3.1. Okay? We need to write the times in the first column of table 3.1, and we need to complete the heading in table 3.1. In 30 seconds interval, mean he will start at 0 seconds, then he will go 30 seconds plus 30, 60, plus 30, 90, plus 30, 120, plus 30, 150, plus 30, it is 180 seconds. Now to label it, it is, to complete the label, it is time in seconds and the temperature initial in degrees Celsius. That's it. In part C, we need to calculate the decrease in temperature between temperature 0 and temperature 90 seconds. So you take the temperature at 0 seconds and at 90 seconds. So do 95 minus 72, we're gonna go down and we are gonna get 23 degrees Celsius. Now calculate the temperature difference in delta seconds between the time to temperature 0, so at the time 0 seconds, and the room temperature. So we're gonna go up. We know that room temperature is what? Room temperature is 22 degrees Celsius. So what is the time at 0 seconds? It is 95 degrees Celsius. Subtract it from the room temperature, which is 22. Doing it on the calculator, you are gonna get 73 degrees Celsius is the change in temperature. So this is 73 degrees Celsius. Now we need to calculate a temperature difference between 90 seconds and 180 seconds. Okay, so here it is gonna be 90 seconds is 72 minus 180 seconds, which is 65. It is 7 degrees Celsius different. We need to calculate the difference in temperature at 90 seconds and at room temperature. So at 90 seconds, what is the room temperature? It is 72. So 72 minus room temperature, which is 22 degrees Celsius, you are going to get 50 degrees Celsius. So we're going to go down and put 50 degrees Celsius. Now in part D, a student suggests that the decrease in temperature of the water in 90 seconds should be greater when the starting temperature is greater. State whether the results agree with this suggestion. Justify your answer by reference to the result. So the student is saying what? There should be a decrease in temperature, okay, from the 90 seconds, and this decrease should be greater when the starting temperature is greater. Meaning, if you go up, take at 90 seconds, 72. Then let's say we took, for example, at 60 seconds. What is the temperature difference? It is 78 minus 72, which is 6 degrees Celsius. But if we took from 90 seconds and 0 seconds, now the time difference is greater. Okay, what is the difference? It is 95 minus 72, which is 23 degrees Celsius. So yes, it does work. What he is saying is correct. So yes, he is correct. His statement is correct. And then what I wrote over here, okay, you can copy it and put it the same over here. Now, part 2. Suggest how you would continue the experiment using the same apparatus and method. Just use more timings. So continue experiment after 180 seconds. Okay, now 180 seconds, my bad. Okay, now here, until temperature is equal to room temperature. If you write this, you are gonna get the 2 marks, okay? One for this and one for this. Now, the last question. Refer to table 3.1. Estimate the temperature of the water in the beaker after cooling for 90 seconds. So we are gonna go up. So what I'm gonna do is a long process. If you, of course, have an easier way to do it, then use it. But how I'm gonna solve it is I'm gonna take the final temperature, 65 seconds. Now what I'm gonna do is I'm gonna subtract it from the temperature they told us. They told us from 90 seconds, so they added an additional 90 seconds. So at 90 seconds, the temperature was 72. So 65 minus 72, doing it on the calculator, you are gonna get minus 7. Now, this is not where we stop. What I'm gonna do next is I'm gonna take, again, the temperature here, 65, and I'm gonna add or subtract this over here. So minus 7. 65 plus minus 7, do it on your calculator. You are then gonna get 58. So this answer is then correct. Going down, if you write 58 degrees Celsius, it is correct. Because if you look at the answer key, it says between 59 to 63 degrees Celsius inclusive. Meaning if you got 59, if you got 63, anything in between these numbers, it is correct. So that means 58 is correct. Thank you guys for watching. I hope you understood and have a wonderful day.